Okay, and the last thing we have to review about merge sort is the complexity. So let's review the complexity of this algorithm. So this is the code for merge sort. We already saw it in a previous video. And we are going to find out how many operations you have to perform in every step. So we can have an idea of how the execution time is. So the first line is calculating the length of the array. So for sure, this is going to take n operations because you have to count one by one how many elements the array has before being able to know the length of the array. So this is n operations. And if we assume that one operation takes 1 unit of time, it's equivalent to say that this takes n units of time. Then we have to check this condition. We are going to assume that this takes one operation, a unit of time, constant time anyway. Checking this condition, it does not depend on the length of the array. And then we are going to assume that we enter the else, because this is the worst case. This is where we must do the most work. So just doing an assignment, it takes one operation. It's true that this also takes maybe a couple of operations, but we are going to assume just it's one because it's constant time. And then we have to go for merge sort again. So if this merge sort takes a time as a function of n, this is going to take a time which is a function of n divided by 2, because it's half of the array. And the same thing is going to happen with the next line. And then we have the merge. In the merge, in the worst case, we have to check every element in every list and copying it to the final list. So this is n operations, because at the end you have to copy all the elements. So the merge is going to take that amount of time after you have returned all this. So merge sort, it takes, if you sum up all this, this is Tn. So Tn is twice this 10 of n divided by 2 plus 2 n operations plus 2 operations, but we just ignore the constants. So we have this expression. This is the expression, the recurrence relationship for the execution time of merge sort. So now we have to find out what the complexity is based on this expression. And there are two ways of doing this. The long way is building the recursion tree and summing all the elements of the recursion tree. The short way is applying the master theorem. So let's go for the long way first and then the master theorem. The long way is building the recursion tree. So we start with this fixed amount of not recursive expression. This is n. And then we have twice n divided by 2. And then we go again divided by 4, divided by 8, etc. So when we build the recursion tree, we have to make sure we realize what the patterns are. So here you can see that this is 2, 4, 8. So the pattern is, this is 2 to the 1, this is 2 to the 3, 2 to the 2, 2 to the 3, and so on. This is the first pattern. Then you know that this level has 2 branches. There are 2 elements here. At this level we have 4 branches, 2 to the 2 elements, and so on. So this is another pattern. And this tree finishes when you get to 1 element list. All the recursion trees finish when you cannot, the recursion trees, when you divide things, they finish when you cannot divide anymore. So you get to 1. So we have to find one way of expressing this 1 in this way. So you can use the pattern. Okay, and this tree has 1, this level, plus 2 to the log n divided by log 2 levels. So at this moment you can have 2 questions. How do you know that the last level has this amount of branches? And how do you know that the value of every element in this last level has this form? Okay? Well, the last level is made of 1s, because you have list of 1 element. This is when the recursion of merge sort finishes. So your recursion stops when you cannot divide by 2 anymore. Given that at each level the elements have this form, so if you go back to the tree, you can see that at this time this is n divided by 2 to the 1, n divided by 2 to the 2. So this is the generic way of expressing the element of the tree. So you can say, okay, in the last level, I still have this form, but the element is equal to 1. So here we have an expression, and then we can solve this equation to find out the value of I. So we solve this, we apply the logarithm, and we get the I is log to the n log of n divided by log of 2. So in the last level, the form is n divided by 2 to the y, with y as this, okay? So after we know that, what we have to do now is to find out what the sum of all elements is. So Tn is n plus all this. So from the first to the last level, from this level to the last one, I have to sum up all the elements in the level. So in the first level, there are 2 elements. So 2 to the 1. And each element is n divided by 2. So when I is 1, you have 2 multiplied by n divided by 2. When the level is 2, you have 2 to the 2, 4 elements, 1, 2, 3, 4. And each element is n divided by 4, n divided by 2 to the 2. So this is the expression for the elements in the level, and this is the last level. So this is the equation you have to solve. But then here you realize that this is really simple because this expression cancels out with this. So you just get n here. And when you have a sum that does not depend on the index, this is just the multiplication of the content of the sum by the limit of the sum. So this is n plus n multiplied by log n divided by log n. And because we are interested in the complexity, we just ignore the constants and we ignore the low order values. So this is n log n. And this is one way of showing that merge sort is n log n. The short way is just applying the master theorem. For that, we have to check that this equation has this form, and it has. Next, we review the cases. So we find out that what the values of a and b are. These are. We calculate log base b of a. This is 1. And then we answer the question whether f of n, which is n, is lower than n to the 1, is equal to n to the 1, or higher than n to the 1. If you do not understand what I'm talking about here, please watch a video about the master theorem. And given that this is exactly this, we are in case 2. And when it's case 2, this is the complexity, n to the log ba, which is 1, multiplied by log n. So we again get theta of n log n, which is exactly the same result we got with the recursion tree.